All right, we're continuing in section 3.4. We're going to look today at some more addition subtraction algorithms as it pertains to other bases. Then we're also going to look at mental estimation today, okay? So we're going to take a look at these algorithms that we did last time, but we're going to apply them inside of a different base. And so the first one we're going to take a look at is base 8. So if you remember, base 8 has the numerals 0 through 7. Okay, so there's no 8s, 9s in base 8. And we're going to look at how we add 3, 4 base 8 to 1, 7 base 8. So when we did this last time, we went through a bunch of different methods. One is just the standard algorithm. One was a lattice algorithm. One was a partial additions algorithm or something like that, I think we called it. And so scratch addition, that was another one. So we're going to look at this in a variety of ways. The idea is for you to get a little bit uncomfortable with what you think is the easiest way to do this problem. Because you're very comfortable and familiar with the standard algorithm. It's the one that you grew up learning, and it's simply not the only one that's taught anymore. And you have to get beyond yourself to realize that it may be the best way for you to have learned it, but it may not be the best way for little Johnny in your class to learn it. Okay? So that's kind of what we're doing today, is we're putting ourselves in the position of the kids who are seeing this, and we're doing it because we're using a base that we're really not quite as comfortable and familiar with. Make sense? Okay, fantastic. So we are going to do this with the standard algorithm first. So we've got 3, 4, and 1, 7. And the catch is this. If we add with the standard algorithm, what is it that we add first? The ones place, right? The 4 and the 7. Now, 4 plus 7 in base 10 is 11, right? But we don't get to do that in base 8. So there's a couple of things you could do. And you could do essentially what the children would do when they count on their fingers, right? So we're at 7, and then we do 8, 9, 10, 11, right? So you're at 7, and you can go 1, 0, 1, 1, 1, 2, 1, 3. Okay? Or you could write it down. In other words, what you could do is you could figure out what comes after 7. And count 3 places over. Let me actually change a color here. So here's 1 place, 2 place, I said 3 and I meant 4. 3 places and 4 places because we're adding 4. This is actually the number 1, 3. So what do? Well, we write down a 3 and we carry a 1. Now we're just as happy at this point to add 1 plus 3 plus 1 because that stays within this base and gives me a 5. Now anytime you're working in another base, you need to write the base subscript next to it. So this would be 5, 3 base 8. Let me show you another way that you can process the 4 plus 7, okay? 4 plus 7 is 11, correct? But in base 8, how many 8s are in 11? 1, so that's why we carried the 1. We carried 1 8. How many are left over from that when I have 11 items and I take 8 away? 3, right? And that's the 3 that gets left here. And that's actually also what some people do when they're adding like this, right? They get 15 and they carry the 10 and they write down the 5. Okay, so both of those ways of processing are ways that we do process this in base 10. So either one would be options if you're working with the standard algorithm with the base addition. So I'm going to, looks like I did scratch addition here. I don't know why I did that. Let's do left to right addition because that makes more sense with 2 digits. All right, so if we do left to right addition, we'll start with the leftmost number. And we can add 3 and 1 just fine to give us a 4. And then there's a 0 here. You can dot it or draw it in. It doesn't matter. But there's a 0 here because I'm just adding the 8's place. And then when I do the 4 plus the 7, I have the same problem, right? 4 plus 7 is 11. Either I have to count up from the 7, or I can say 11 is how many 8's? It's 1 8 and 3 left over. And then I have one more step to add these pieces together to get 5, 3 base 8. So this one I chose to do is left to right, L to R. Now there's nothing, I'm going to say that's not true. There are places in your book where it tells you which algorithm to use, and there are places where you can pick whichever one you want, okay? So I'm just going to show you a couple of options on each of these because as you can see, there's no directions on this page. Because I wanted to leave it very flexible so that we could experience some different options as we're working through them together. And then that way when you get to your homework and your group work, you'll be able to do some of those moving in and out of it as they tell you to or as you choose to. Okay? Let's do a different one. I think the next one's subtraction, indeed. Okay, so we have 3, 4 minus 1, 7 now. Okay, so again, standard algorithm first. And we're going to do something that feels a little bit funny. And every time I do it here, people think that looks funny. I don't think you're allowed to do that. But you do it all the time with your standard algorithm, which is interesting because you don't think it's funny over there. Like funny as in weird, not funny as in like laughter. Okay, so we can't take 7 away from 4, right? So what is the word that we use usually when we're trying to allow ourselves to do that? Borrowing. And the word that's sort of like the pop word you see in the curriculum now is regrouping, just so that you're aware. You're regrouping. You're taking something and you're regrouping it into a different location. So everything that my 2nd grade son comes home with says regrouping on it, and it flusters my husband because that's not the word. The word's supposed to say borrowing, right? Well, it's regrouping. So you're going to see a lot of regrouping on your textbooks these days. So when we borrow or we regroup, we take the 3 and we make it a 2. Now, in base 10, when we borrow 10, right? Because you're taking from the tens place and you're moving into the ones place. It's like taking a dime and turning it into 10 pennies, right? Okay. But in base 8, what are we going to be borrowing? 8. Okay, we're going to be borrowing 8, and we already have 4. So what is 8 plus 4? 12. Now, when I write the number 12 here, it is a base 10 12. It is 12 individual 1 objects. Okay, we're writing down 12. And when we subtract, we're subtracting 12 minus 7. And what is 12 minus 7? 5. So there's no problem at that point. And 2 minus 1 is the 1. And this is in, again, base 8. So the pushback I usually get here is, well, why did I write down 12? I'm supposed to be working in base 8. But you guys do this in base 10 all the time, right? If you would have borrowed this in base 10, you would have either put the 1 right beside the 4, or you would have marked the 4 out and written 14 above it. Are you allowed to have 14 1s? Well, not really, right? We don't usually write it that way. We write a 1 in the tens column and a 4 in the ones column. But you do it when you're in the middle of subtraction, right? For just this split second, you're sort of like allowing yourself to put it there. The same thing's true here. For just this split point in time, we're allowing ourselves to put the 12 in that location to do the subtraction. Okay, so it's the same thing. Let's do equal additions on this one. We stopped off on that one last time. Let's see if you remember what it is. What is the whole goal with equal additions? Do you remember? Or good. It's not borrowing. Okay, so we do not want to borrow. No borrowing. So in particular, what we want to do is we want to get lots of zeros, because zeros are wonderful to subtract. We like zeros. Zeros are friend. So in other words, this 1, 7 at the bottom, I don't want it to be a 1, 7. I want it to be something and a 0. So what would I have to add normally in base 10 to 7 to turn it into something different? A 3, because 7 plus 3 turns you into 10, and you can carry it over and so forth. You can regroup. Okay, but we're not in base 10. We're in base 8. So what would I have to add to the 7 to get to a something and a 0? Just 1, right? And the reason it's just 1 is because the number that comes after 1, 7, right here after the 7, would be 1, 0. It's 1 more. It's 1 place over. So if I add a 1 to the 1, 7, I also need to add a 1 to the 3, 4. So what is 3, 4 plus 1? 3, 5. That's the easy one. What is 1, 7 plus 1? 2, 0. Okay? Because the 7 has to carry over into the next column, the 8's column, by 1. And the 7 itself becomes a 0. So this would be minus 2, 0. And what is 3, 5 minus 2, 0? 1, 5. No borrowing, so we're done. A little weird, right? A little weird. We're going to change bases because at this point you might be getting a little bit too comfortable with base 8. Maybe. You know how you get base 8, right? No thumbs. That's how you get it, base 8. Yeah, just so you know. All right, we're going to look at base 3. Base 3 has 3 digits, 0, 1, and 2. We're adding the numbers 1, 2, 1, 2 and 1, 1, 2, both in base 3 together. So let's do the standard algorithm first. And then we're going to actually do lattice on this one next. Okay, I do the standard algorithm. There's a problem because on the right-hand side, 2 plus 2 is 4, and that's not okay, right? So let's think about it the way that we do how many, this is base 3, so if you have 4, how many 3's are there in 4? There's 1, so I'm going to carry a 1, and how many is left over? 1. The number 4 is 1 3 and 1 left over because you've regrouped them into groups of 3 and leftovers. Now, we've got this column, this second column, that we've got a 1, 1, and 1. This is the 3's column. What is 1 plus 1 plus 1? 3. There's no 3's in base 3, correct? And if I regroup them, that becomes 1, 3. So I'll carry the 1, and how many are left over? 0. Good job. I'm going to do the same thing again. I've got 1, 2, and 1, which gives me 4. So 4 is 1, 3 with 1 left over. And then I have 1 plus 1, which is 2. And always be sure to the very end, remember to write the base next to the value as a subscript. It's supposed to look small. Mine's a little bit large, but that's okay. Base 3. Let's look at lattice. All right, so we have 1, 2, 1, 2, and 1, 1, 2. And we draw a box. That's a really thick box. Let me change the size of that. Okay, and then you're going to split the box into 4 parts because there are 4 sets of numbers you're adding, and divide them along the diagonals. The addition itself you can do left to right or right to left here, doesn't matter. We'll go from right to left just because we've already been thinking about that. The bottom corner in each box is the 1's place, and the top corner in each box in this case is the 3's place because we're working in base 3. So when we add 2 plus 2 and we get 4, that is 1, 3, and 1 left over. We add our 1 and our 1 and we get a 2, so that one's cool. That's just plain old 2 down here. 2 plus 1 is 3, which is 1, 3, and 0 left over. And then the 1 can just come straight down. So what we do next is we extend the diagonals from the lattice. It's kind of sloppy, but you get the idea. And here it does matter that you move from right to left. So this 1 right here in the bottom diagonal will be a 1. The second diagonal here is a 2 and a 1, which is 3. Still no 3's, right? So we have to regroup by carrying a 1 and writing down that we have 0 left over because it's 1, 3, and 0 left over. Here I have a 1 and a 0. So 1 and 0 is 1. And then I have, along my last diagonal with numbers in it, I have 2 1's, so it's a 2 here. So I have 2, 1, 0, 1, base 3. And addition is not complete without subtraction, so we're going to try subtraction 1 with base 3. Okay, so standard algorithm, I have 1, 0, 0, 2, minus 1, 1, 0. All right, so for starters, I can do subtraction. There's no problem with that one, right? On the right-hand column, the 1's place, I've got 2 minus 0, and lo and behold, it's still 2. But there's a problem after that, and it's like a double problem because there's 2 zeros, right? I can't borrow from a 0. It doesn't work. There's nothing to borrow from if I don't have anything. So I actually have to go all the way over to this 1 to borrow. So what will that 1 become? A 0. And when you borrow in base 3, how many do you borrow? 3. So this 0 becomes a 3. And that's all well and good, but I actually need to borrow from that 3 as well, because the 0 just next to it in the 3's column is 0, and I need it to be something. So we're going to cross this 3 out. It'll make it a 2, and this 0 will become a 3, because when I borrow in base 3, I borrow 3. So that's all the borrowing that I need to do, and I can actually do my subtraction now. In the 3's column, I have 3 minus 1, which is 2. In the 3 squareds column, I have 2 minus 1, which is 1. and there's nothing left to do on the 3 cubes column. I do need to put a base 3 at the bottom down here, and then I'm done. Okay? So let's do equal additions with this one again. Okay, so we have 1, 0, 0, 2 minus 1, 1, 0. Okay, so there's absolutely nothing with the tens column that I need to worry about, or sorry, the ones column that I need to worry about. But the threes column right here, this spot, I got issues. I need to add something to that 1 in order to make it a 0. What would I have to add in base 3? A 2. But it's a 2 in the tens, which would have been the tens, the threes place actually now, right? In the threes place, so I have to add a 2, 0. Okay, because my goal is to fix this problem. If I just add a 2, it's actually going to change that number, and that's not helpful. Does everybody get that? Okay, so we're going to actually do the addition so that you can see that it actually helped. So on the top number, I end up with 1, 0, 2, 2. Right? And on the bottom, what do I end up with? Well, there's a 0 here, and my whole goal was to get a 0 here, so that's fantastic. But what happens in front of those 2 zeros? In other words, what happens when I add this 1 and this 2 together?
You get a 3. So that's
I get a 3.
and so that's going to be a 1 to be carried over to the other one.
Right. I'm going to have to carry a 1 over to the next column. All right? So what in the world is happening is, well, I end up getting a 2 here. I have to carry over a 3. I carry a 1. I mean, I carry the 1 over to the next column. But I'm not done. What's the problem now? I still have to borrow, right? If I continue this where I am, I'd still need to borrow because this spot right here, let me shade it in. It's very light green. I don't know if you can see that at all. But that very light green that I shaded has a 0 minus 2 in it, right? So I can't do the 0 minus 2. So what would I need to add to the 2 in the third place over? A 1, which would be the equivalent of 1, 0, 0. But if I do it to the bottom number, I have to do it to the top number. Okay, so the top number, that's simple enough. That's 1, 1, 2, 2. Nice. What happens to the number 2, 0, 0 when I add 1, 0, 0 to it? You get a 1 with 3 zeros. Looks like the number 1,000. It would be 1, 0, 0, 0. Because 1 plus 2 would be 3, which is written as a 0 and carry a 1. Okay? Can we subtract now?
Yes.
Yes, because there's lots of zeros everywhere. Fantastic. I feel like, oh, I was remembering the last problem. So we're good. All right, so if we subtract, I get 2 here, a 2 here, and a 1 here, and then the ones in the very beginning cancel out, and this is base 3. All right. We're all good? Okay. There's 2 items that we're going to do still left in this section. We're done with other bases. Can I get a name in? Okay. All right. We are going to work on mental math and on estimation. And those are not 2 things that are always together or always separated. Okay? So mental math does not mean if I'm doing it in my head, I have to approximate. Something that's really important for you to realize. Okay? Mental math just means I can do it in my head. Here's the catch about mental math. If you're doing it in your head, I can't grade what's going on in your head very well. Make sense? So when we're writing the things down, we're writing it for the benefit of me. That's really all you're doing. You're really not writing it because it needed to be written. So if you find yourself writing something down and really relying upon it to do the problem, then you're probably not using mental math. Okay? The writing it down is really just the showing what's going on in your brain so that I can grade it. So let me take a look with you and we'll show you some different mental math techniques. All right, so one mental math technique, and so this section, let me say one more thing. This section is more about the efficiency, how quickly we can do something, as opposed to why it works. We've been doing so far is we did a lot of why it works and how that process is going. What does it mean when we're regrouping, that kind of stuff. That's not the goal of this. The goal of this is to be able to do something quickly in our head. Okay, so we're not focusing on why does it work. We're focusing on how quickly I can get it done. All right, left to right. Left to right actually takes the very first two numbers and thinks about them and adds them together. So the 46 is actually the number 40. The 38 is actually the number 30, and we add 40 plus 30 together and we get 70. And then we do the same thing with the other pieces. We say 6 and 8, and we get 14, and we add together, we get 84. Okay? So you should be able to process through that. Close your eyes and think about it. Can you do it in your head? Can I add 40 plus 30 together? Yeah, you guys can do that in your head. That's 70. And you can remember, you couldn't remember a whole long list of these things, but you can remember 70. And then you add the 6 and the 8 together, and because you learned flashcards somewhere along the way, you know that's a 14. And then you should be able to take 70 and 14 to get 84. That's what this looks like. Okay? On paper, it looks like what I just wrote down. But really, this is something you should be able to process in your head. Like if you're dealing with like a 4-digit number, that's something different. We're not talking about 4-digit numbers here. These are 2-digit numbers. Okay? This is left to right addition. The next one's called breaking up and bridging. So breaking up and bridging looks something like this. You don't change the 46 to being 40 and 6. You leave it as 46. But you do break up the 30 into 30 and 8. So you take the 46 and you add 30 to it, and you recognize 46 plus 30 is 76. Which means you've done most of the work, right? It doesn't get a whole lot bigger than that, because now what you need to do is you need to add the 8 to the 76. 76 plus 8 is 84. Now, notice a few things on even how I'm writing this, though. Notice, and we've talked about this before, but I'm going to talk about it again. Notice I don't write 46 plus 30 equals 76 plus 8 equals like that. It's not written all in one line of equalities, right? It's not. You've broken it apart into a fact. The fact is right here, 46 plus 30 is 76. And then I used a separate line to do the next part of the addition. Okay, so don't write equals, 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 meaning and the next part is. That's not what equals means. Right? All right, the next one is called trading off. Trading off feels a little bit like equal additions. So remember with equal additions, it was a subtraction problem first of all. With a subtraction problem in equal additions, as long as you added a number to the bottom number and added the number to the top, it didn't change everything, right? Everything was the same. We talked about the equivalent of being if I stood at the front bare feet and Catherine stood at the front bare feet and then we both added 2-inch heels, it wouldn't change the difference in our heights from when we were barefoot, right? That's equal additions. Trading off is the idea of doing a scale. Okay, so imagine a scale, it's balanced. If you take something off one side, then you have to actually compensate somehow. Okay, so a scale works well for subtraction, but not so well for addition. So let me show you how it works for the addition part here. Here's 46 and here's 38. Now 38 is, of the two anyway, closer to the next number up. Agreed? I mean, it's closer to 40 than, say, 46 is to 50. So the idea would be adding something to one or the other number. 38, it would be nice to add a 2 to it, because then it turns into something with a 0. Remember, zeros are our friend? But if I add a 2, I also have to balance it by subtracting a 2. So if you think about the scale and you're weighing some kind of a fruit, if you add 2 pounds of oranges, you would have to take off the 2 pounds of apples to have the same poundage of fruit when you were done. Make sense? That's what we're doing here. We're adding it in one place and we're taking it off in another place to balance it. It's the same thing that happens if you guys, and hopefully you have learned or will learn shortly, how to do a budget. Right? Budget is just telling your money what you're going to do with it. If I actually decide that I'm going to spend $10 on those pair of shoes, I got to figure out where that $10 is coming from, because a credit card's not a good choice. Right? It means I'm going to spend $10 less eating out this week or whatever. Okay, it's a balance. If you take it away from someplace else, you got to give it back somewhere. So this is what's going on here. So the cool thing is that you end up with numbers that are easier to work with, which is the whole point. So what is 46 minus 2? 44. And what is 38 plus 2? 40. And is it easier to add 44 and 40 together than 46 and 38? Yeah, it's a lot easier. So this works really well when numbers are kind of close to another value. So if you had both the numbers that were like 46 and 45, it doesn't really work super well. But this one was really nice because 38 is pretty close to the next number. If you had the number 41, same thing. You could take away a 1 and it'd be pretty close to where you want it to be to give you the other number. So this is called trading off. All right, compatible numbers. Again, doesn't always work super well, depends on the numbers you're working with, but sometimes, and when it does work nicely, it is really nice. So the idea is putting the numbers in a different order where it's easier to add them together. Okay? So like, let's just take the number 40 here. What is the nicest number in this list to add to 40?
60.
60. Why are those so nice? Because they make 100. So we're adding them, if you will, out of order. We're just going to go down the list. What about the 30?
70.
70, because they also add together to be 100. That looks like a 180. It really wasn't meant to. Try that again. Okay, and then I didn't get the 50 in there, so I need to. And then what's 100, 150? 250. Now, I use this strategy when I'm grocery shopping. I don't do it with precision. I don't make sure that I'm exactly right because I know I'm going to have to pay tax at the end anyway. But I do. I kind of keep track of what this was a 30-cent item and this was a $1.70 item. Together they add to about $2 kind of thing. And of course nothing works out perfectly because they put nines everywhere on top of all your grocery items, don't they? You guys know what I'm talking about. But you round in your head and you just pretend like it's not a 9. Okay, same idea. So this is something that I actually use in the grocery store a lot. Now, if you don't have compatible numbers, you can also make compatible numbers. So let me show you how that works. 35 and 68 are definitely not compatible, but they're close. They're close. If I took 35 and I left it as 35, what would I like to add to it to give me a nice, beautiful 100?
Oh, do you get 100?
65, yeah, 65 would be it. And that's not exactly what I have, but it's awfully close. This would give me 100. How much did I not add that I should have? 3. So this is now 103. And if you didn't want to work with the 35 and the 68, you could have worked it at the reversed. You could have said, okay, I'm going to start with the 68. So 68, what do I need to add to it? Well, I need to add to it 32. That's what it would have been, right? And then add the 3 on afterwards. So you could do it in reverse order, which would be totally cool. All right, breaking up and bridging with subtraction. Okay, we already did breaking up and bridging with addition. Beautifully, the same thing as subtraction. So we're going to take that same 46 that we had before, and just before when we did breaking up and bridging, we added 30 to it. So we're going to subtract the 30 from it. What is 46 minus 30? 16. Breaking up and bridging is fantastic with subtraction as well because it's automatically getting smaller, and smaller numbers generally are easier to work with than larger ones. Because then it's 16, but I didn't take away what? The 8, right? And you know 16 minus 8 because the numbers were smaller and they're easier to work with, so then you end up with an 8 when you're done. Okay, now trading off with subtraction is exactly the same as equal additions. Okay, so this is just another name for it. Okay, so if you remember, the whole idea is that we're not borrowing. So 46 plus 38, minus 38. We don't want the 38. We want to make it zeros in the ones column. So what would I need to add to 38? Again, we're working in base 10, so this is nice now, right? 2. Okay, but with subtraction, if you add 2 in one place, you add 2 in the other place. Okay? With addition, it was an add one piece and subtract the other piece. Okay? You're balancing it. And you're really balancing it here too. It's sort of hidden, but this plus 2 is really got a negative in front of it. Do you see that? This is really a minus 2. It's just hiding. So you've really got a minus 2 down here and a plus 2 up here. They're balancing. So we have 48 minus 40, which is much easier to subtract than 46 minus 38. And you get your same 8. Okay, last example that is mental math with actually computing exact quantities. Drop the zeros. And you've probably thought this without actually thinking that this had a name before. The zeros on the end match, and they're very unuseful. They're just sort of like a nuisance, right? They're just holding a place. So this is very much like taking 46 minus 34. And if you subtract 46 minus 34, what do you get? 12. So your answer is the same 12 with the zeros that you ignored put back on. So you're just ignoring the zeros for a moment. All right, everything else that we're going to look at now actually has the word estimation in it. So you're going to see a lot of the same strategies that we did, but our answers here are not going to be the right answers. They're just going to be approximations. Now we might get lucky and actually write down exactly the right answer, but that's not the goal. The goal is to get pretty close. So sometimes we're just going to ignore something. If you're really calculating something exactly, that's not okay. You can't just ignore it. But in this section, we're estimating. Our goal is to get an approximation only. Okay? So please be very careful, both when you do this homework assignment and then when it comes to the time that you take this test as well. Because I always have students get those two things confused. Mental math does not mean estimation, and estimation does not mean it even has to be in your head. Okay? Estimation can be done on paper. Mental math should give you exact answers. So they're not the same thing. All right, so let me show you the first one. This is called front-end estimation with adjustment. So there's two steps to this because you see it says front-end estimation, and then it says with adjustment. You guys see the two pieces here? All right. So front-end estimation does the following. It takes the first digit and it adds them together. So this is 300, 400, and 200. What do you get when you add 300, 400, 200? 900? Excellent. Now, adjustment does not mean do the same thing with the tens digit, and it certainly doesn't mean then do the same thing with the ones digit, because if you do the same thing with the tens digit and the ones digit, you're finding the exact answer. That's not the goal. The adjustment means taking what's left and looking for compatible numbers. So within this that's left, what looks like they're approximately compatible? Like they're close.
62.
32 and 62 are awfully close to what? 100. They're awfully close to the number 100, right? 32, 62, you're close. You're not exact. If you add that really quickly, you probably realize you're at 94. It's not exact, but you're close. So these two numbers are close to being compatible and approximately 100. And then the 25 is fine to just leave 25. If you want to change the 25, like let's say that we're in a 25 and it were a 46, and you wanted to change the 46 into a 50, okay, fine. That doesn't hurt anything. You could do that. But you're not really adding it or subtracting it to anything. You're just going to include it. So I've now got 900, 125. Well, 900 and 100 is what? 1,000. So I end up with 1,025. And this is an approximation. I'll put that there just to remind you. We didn't try to find an exact answer. We were trying to approximate it without finding an exact answer to make it easier on ourselves. Okay, same idea on the second one with this whole idea of grouping nice numbers together. So this is like the compatible numbers, but you're just looking for the ones that seem to be close to compatible. They're almost able to be grouped, okay? And your grouping and mine might not be exactly the same. So I'm just going to start with my 42. What would you like to add to the 42 or group with the 42? 64? All right. These two are approximately what? They're about 100. All right, our next number, 35. You would probably group it with the 71 because those are approximately 100. Now, the only one that gets left out of this grouping happens to be the 55. So you can leave it 55, or you could say it's about 50. That'd be okay too. So I would be inclined to probably just go with 50 and say we're at about 250. I say that, and I'll tell you my paper here says 255. Okay? Is either answer okay? Yeah, this is an approximation. It's fine. There's nothing wrong with that. Okay? All right, clustering. Clustering doesn't work for everything either, but it is a really nice strategy when it works. Clustering is the idea that all of the numbers are pretty close to the same number, like a common number among all of them. All of these numbers are awfully close to what? 500. I mean, some are closer than others, but these numbers are all pretty much 500. Right, so this would be like going to the grocery store and everything you grabbed was awfully close to $1, so you just count how many things are in your basket, right? Like, 15 things, this is going to be about 15 bucks. Same idea. So all of these are about 500, and how many numbers are there? 5. So depending on what level the kids are at that point, if they know multiplication, they can just do multiplication 5 times 500, or they can simply add 5 500s together, which would be okay too. So what is 5 times 500? 2,500. Again, these are approximates, right? Okay, 2 last examples. First one's called rounding. And I'm guessing you probably remember this one. The trick is this. Sometimes your book just says round, and it doesn't say round to what. That's not real helpful, is it? Well, but you get to decide. So maybe it is. I don't know. So let's do a couple of times on this problem. One where we're rounding to the thousands place. And just for argument's sake, one where we're going to round to the hundreds place. So you can see that it has more than one option, I guess. Okay, so the 4,700, actually let me do this, oops. The 4,700 in the thousands place has a 4. So you start with that place. It's either going to stay a 4 or it's going to become a 5. Those are your only choices, okay? Stay a 4, become a 5. The way you decide is you look at the next number over. It's a 7. If that number is 5 and up, it moves up to a 5. If that number is 0 through 4, then the first number will stay a 4. Okay? 5 and up, you round the number before up. 4 and down, you leave the number the same. So the number 4,789 will become 5,000. Okay, so let's practice it again with the 3. The 3 is in the thousands place. So we look at the 1. This 1 is actually below 5. It's between the 0 to 4. So does the 3 become a 2? No, it does not. The 3 will stay a 3 because the whole number is rounding down to 3,000. It was originally 3,148. Now it has been rounded down to 3,000. The idea being that it's very easy to subtract. I think we're subtracting. Nope, we're adding. It's very easy to add 5,000 and 3,000, whereas the first numbers were messier. So it is 5,000 plus 3,000. 8,000. Okay. Let's do the hundreds place. Same process. Let me clean this off. All right, so we're going to be looking at the 7 by looking at the 8 next to it. So this 8 means that the 7 I underlined will do what? It will go up to the next number up, which happens to be an 8. So the 4,789 will become 4,800. And then the 1 in 3,148, we look at the 4 here, and that 4 says what's going to happen to the 1? Will stay the same. So 3,148 becomes 3,100. And this isn't too bad. I still have lots of zeros. Zeros are good. So if I add 4,800 and 3,100, what do I get? 7,900. Still not precise, not exact, but it's also still close to the 8,000. Notice that, right? Yeah, it is. Okay, our last strategy is not even going to give us one answer. How unhelpful is that? I don't even get a single answer. I'm going to get 2 answers. All right, so this is called using the range. So who has heard the word range before? Okay, there's lots of places you can hear the word range. So somebody tell me one of them.
Maybe like the scores, like an A is between a 90 and a
Okay, so a grouping of scores. Where else have we heard the word range before? Okay, that's the same thing like Catherine was pointing out. That's true. Where have you heard about it specifically used in mathematics? Okay, that's the one we're going to use. There's 2 other places. Usually somebody says something like domain and range, right? Graphs, algebra kind of stuff. Has anybody taken a statistics course? Yes, okay. Has anybody taken proportional and statistical reasoning? A few of you have. Okay, so we talk about range in there as well. We talk about the numbers that we've got with the smallest and the least, kind of like Beth mentioned. That's kind of what we're going to look at here. Okay, so the range here is going to look at these numbers and round everything down. So 370, we're going to look at the first number, okay? So it'd be the hundreds place. 370, if I round 370 down, what does it round to? 300. And if I round 647 down, what does it round to? 600. Okay, so that's good. This totals to 900. Wonderful. How about if I take 370 and I round up, what does it become? 400. And if I take 647 and I round up, 700. So what's 400 plus 700? 1100. The range is between 900 to 1100. Basically what you're saying is that the true answer to this addition problem lies somewhere between the lower end of what's possible and the upper end of what's possible. It's somewhere between 900 and 1100. And that's not a bad thing to do when you're looking at problems like these anyway, especially when you're estimating, to look back and be like, does that estimation make sense? I'm not going to find it exactly, I don't need to, but does it make sense? Because if I gave you this question and the answer you gave me was 2,342 or whatever, it doesn't make sense. It's so far out of the correct range of values that it's impractical. Does that make sense? All right.